Now we come to the next question that came in the IIT JEE 2006. The question says, a solid cylinder of mass m and radius r is rolling down a rough inclined plane of inclination theta. The coefficient of friction between the cylinder and incline is mu. Then, and as you can see, there are 4 options and you have to choose the right ones. This is an excellent question. We will use this question to clarify a few more concepts about rolling. Let's understand the following points. A. If there is no friction, then the cylinder will simply slide down the incline and there will be no rolling. B. For rolling, we need to talk about the axis passing through the center of mass, and in this case, this torque can be provided only by the force of friction. Since the cylinder is rolling down and not sliding, this force of friction cannot be sliding friction. In fact, it is static friction. Static frictional force can never be dissipative. It cannot cause loss of energy. Let's move further and add the forces to the figure. For the linear motion of the cylinder down the plane, we can write mg sine theta minus F is equal to ma, where F is the static frictional force. On the other hand, for the rotational motion, we can write F into R is equal to I into alpha. Now, what is the value of the static frictional force? Is F equal to mu n or equal to mu mg cos theta? Since the cylinder is rolling down the plane, the linear velocity v is equal to r omega. And since both v and omega are varying with time, we can write dv by dt equal to r time d omega by dt, which means that the linear acceleration a is equal to r times the angular acceleration alpha. And therefore, using the results at 2 and 3, we get a equal to f r square upon I, and if we substitute for a in result 1, we get f equal to mg sine theta whole divided by 1 plus mr square divided by I. This is an interesting result. Take a look at it. It says that the static frictional force acting on the cylinder is a linear function of sine theta. But then theta can vary, right? We can have the cylinder roll down planes of different inclinations. So, we conclude that the static friction F also varies as theta varies. Let's take a closer look. As theta increases, the linear acceleration down the incline g sine theta also increases. And to accommodate this increase, the angular acceleration alpha must also increase for the cylinder to continue to roll without slipping. But for alpha to increase, the torque provided by static friction must increase. Therefore, the static frictional force also must increase. And because static friction is self-adjusting, it does increase till it can. But we know that the limiting value of static friction is mu times the normal force, or mu mg cos theta. So, there is a limiting value of theta beyond which the static frictional force cannot increase. It is at this point that the cylinder starts to slip down the incline. So, coming back to our question, options A and B are ruled out. Options C and D are correct. Let's take a look at a few other JEE questions. This one on your screen says, a ball moves over a fixed track as shown in the figure. From A to B, the ball rolls without slipping. Surface BC is frictionless. Ka, Kb and Kc are kinetic energies of the ball at A, B and C respectively. Then, once again, you have 4 options to choose from. Okay. Now, between the points A and B, the ball rolls without slipping. Hence, there is no dissipation of energy. Also, the potential energy mgHa gets converted into kinetic energy. Since the ball rolls between A and B, this kinetic energy is in the form of translational and rotational kinetic energy. Between points B and C, the surface BC is frictionless. So, obviously, there is no torque about the ball's center of mass. Hence, the angular velocity at B does not change after B. It remains constant between points B and C. And therefore, the rotational kinetic energy also does not change after the point B. The translational kinetic energy, however, converts into potential energy as the ball climbs up after B. At C, the linear velocity of the ball is 0, and so is the translational kinetic energy. But we must note that the ball has rotational kinetic energy at point C. Thus, we conclude 1. Although the total mechanical energy remains constant throughout, the kinetic energy is not the same at the 3 points. In fact, Kb is greater than Kc is greater than Ka. And 2. Since total energy at A is equal to total energy at C, we can write potential energy at A plus kinetic energy at A is equal to potential energy at C plus kinetic energy at C. But since kinetic energy at C is greater than kinetic energy at A, hence potential energy at C is less than potential energy at A. Now, this means, therefore, that Hc is less than H.
You must be wondering what I am doing on a bicycle. In fact, what has a bicycle got to do with rolling? Let's try and imagine a simple situation. You are riding on a bicycle on a plain horizontal track and you want to accelerate. So, you start pedaling more vigorously. Now, we know that the acceleration can be caused, according to Newton's second law, only by an external force. And obviously, in this case, that external force is provided for by the friction. The question that I am going to ask is that what is the direction of the force of friction on each of the wheels of the bicycle when it is accelerating? Let's see. Okay, let us start with the front wheel. Fine. Now, when you are accelerating, the front wheel moves in this direction, right? And the only force that causes it to move in that direction or rotate in that direction is the frictional force. And therefore, in the front wheel, the frictional force acts in the backward direction. Okay? Whereas, if you consider the back wheel, now in the back wheel, there is a driving mechanism which is the chain. Okay? Now, let's take a look at it. Now, there you are, I am pedaling and therefore the wheel starts rotating. But the moment I put it in contact with the ground, it stops. And therefore, the friction in this case actually acts to oppose the rotatory motion caused by the chain. And therefore, the friction acts in the forward direction. To conclude, what we are saying is that in the front wheel, the friction acts in the backward direction, whereas in the back wheel, the friction acts in the forward direction.